there. I'd like to thank you very much for the invitation and the opportunity to help the KICHE celebrate this momentous occasion. It's been a real pleasure to have the opportunity to visit Korea for the first time and to get to meet so many Korean chemical engineers at one time. I'd like to take the opportunity here then to tell you a little bit about my perspectives on chemical engineering as it stands today in the U.S. and in U.S. universities. So I'll talk a little bit about how it has evolved. I'll talk a bit about some innovations, in particular some research areas that I found to be particularly exciting. And so I thought, since this was a happy occasion to celebrate chemical engineering, I'd tell you about some of what I thought were exciting areas of research going on in the U.S. Then I'll talk a little more about chemical engineering as a profession, the employment, evolving curriculum, the bio-nano-info issues that have been addressed by previous speakers, and a little bit about future prospects. It's a pleasure to share the podium with such distinguished speakers, and they've already done a good job making many of the points that I have to make. Chemical engineering really came from around the turn of the previous century and was born from applied chemistry and mechanical engineering. You find a variety of departments that rose in the U.S. from mechanical engineering departments and others that came from applied chemistry, as you have here. As was pointed out earlier, unit operations were a key element in the development of chemical engineering, and unit operations have been a mainstay of the profession and the education coming from way back in the 1920s. Then, of course, the need for reactions and development of new products really fueled a lot of work in catalysis and reaction engineering. And then in the 1950s, also in parallel to the development in Korea, the strong emphasis on analysis and applied math really became an important component of chemical engineering. We saw the transport phenomena and transport processes and the real reliance or relationship between chemical engineering and chemical physics, so that we really consider ourselves a science, and chemical engineering science is really what we find our curriculum to be these days. If you look at that chemical engineering science curriculum, it has, of course, the elements that were already pointed out: thermodynamics, transport processes, kinetics and reaction engineering, mathematical analysis, and systems design. And these are really the core components that we've had with us really since the 1960s. I take this opportunity to put a few pictures in my talk, pictures from various sources. In this, it's just an example of a chemical engineering student project, rather than to modeling just a chemical plant, modeling the digestion of a koala as a series of chemical reactors and separators. Koalas are interesting because they live on eucalyptus leaves, which would be toxic to many species, and they separate small particles from large and have a recycle stream, so it provides all the elements of chemical engineering that you need to test your abilities to design unit operations. I also use this opportunity to point out that chemical engineering truly is a global community. And as was pointed out earlier, the Korean Institute of Chemical Engineering is very, very similar to the American Institute of Chemical Engineering. And I think we find a lot of common issues and common bonds. We're pushing our global nature with MIT's Open Courseware initiative. And so right now you can find numerical methods class on the web at this website from Open Courseware. I see chemical engineering really as an interdisciplinary field, and it's really at a crossroads of many disciplines. And again, this is picking up on themes that were pointed out earlier. But you find chemical engineers working with people in all the other disciplines on a variety of problems related to things from energy and the environment to materials and MEMS and bioengineering. It's been nice to have the previous talks give such nice examples of fundamental biochemical engineering and biochemistry, as well as materials and nanotechnology. Why are chemical engineers so innovative? In my view, we always bring to the table our analytical and mathematical skills. And when you talk to anyone who collaborates routinely with chemical engineers or people in other fields who have worked with chemical engineering students, they always say that the students are very well trained in their analytic and mathematical skills. They bring those skills to collaborations with pure scientists, and sometimes that is really the element that makes us unique. The other element, of course, is that we also understand or try to understand chemistry. And we bring chemistry into analytical and mathematical approaches, and so that's a core and a fundamental thing, and it's the heart of our current name. We tend to span problems, as Sang-Tae Kim, Dr. Kim pointed out, that span from many length scales, from the molecular to the continuum, and we span many different applications, from materials to biological systems, as the previous example showed. Chemical engineers are not afraid of complex systems or messy systems, and so sometimes we're unencumbered in ways that our pure science colleagues are by concern for more pure and simple systems, and we get ourselves involved in very complex systems. And as I mentioned before, this involves or brings us into some really exciting and important applications ranging from energy and environment to materials and biotechnology. I decided that since this was a celebration of chemical engineering, I wanted to present some greatest hits. And I intended to get these from all over the country, and I did get a few from all over the country. But of course, a number of my examples come from MIT, so you'll have to forgive me for my parochial presentation. MIT is a very large department, though, of 34 faculty, so I had a great pool to deal with. So I wanted to talk a little bit about some exciting chemical engineering research going on in nanotechnology, microfluidics, catalysis and zeolites, and some dynamic optimization problems. I note that there are strong parallels to what's going on in Korea, and I probably could have put together the same examples from chemical engineers in Korea. I noted there were sessions involving nanotechnology in this conference. What's exciting to me about nanotechnology, being a co-ed and surface scientist myself, is that now we're able to recognize and make use of very simple and fundamental physical surface forces to allow us to move into more complex systems using very gentle processes. In particular, Paula Hammond and her colleagues at MIT provide a nice example of how one can take a couple of useful approaches in surface science, put them together, and create some really new and exciting structures. Paula takes her background in making microscopic rubber stamps, polydimethylsiloxane stamps, to imprint patterns onto metal surfaces. If you imprint this pattern onto the metal surface, you can get microscopic resolution of the pattern, and you can provide chemical heterogeneity on the surface. She then takes her other field of expertise, which is multi-layer or so-called layer-by-layer adsorption, and she can dip this patterned surface into alternating positive charged or negatively charged polyelectrolytes and make one layer after another of polymer on the surface. She then can add to that by adding colloidal particles to the mix, and now in a beaker she can get a structure as complex as this to self-assemble. Everyone has mentioned the importance of different length scales. Now you have the ability to make patterns on certain length scales of several tens of microns, for instance, with particles that are perhaps maybe 1 micron in size, and those particles may have micropores or nanopores in them, and so you'll be spanning quite a few length scales now in one particular material. I have some examples of these types of structures, again noting the length scales, that you can have a pattern on tens of microns, particles on submicron, and you could have pores within those particles and make interesting optical, electrical, or biofunctional materials. What's really exciting is this takes advantage of self-assembly and simple forces of electrostatics, using positively and negatively charged polymers, using positively and negatively charged particles, using hydrophobic forces, hydrophilic forces, and all of this is feasible now to be done basically in a beaker rather than in a complex machine or device to make a nanostructure. She goes further and shows that it can be done in a beaker and that the particles will sort themselves out if you carefully craft such a surface that has a pattern on it, make the layers of the appropriate charge and the appropriate functionality using these simple forces, hydrophobic, hydrogen bonding, electrostatic forces. You can now again work with multiple length scales, multiple materials, and cause structures to self-assemble into these unique and interesting structures. I realized at one point that everything I was talking about was very small, so one could say that I'm seeing the future of chemical engineering as shrinking. I think Dr. Kim pointed out that that was an important and necessary step, but I see microfluidics and microreactors as an extremely exciting and important area going on in chemical engineering currently. What's been exciting to me, actually, in preparing this talk and learning more about some work in microreactors is that I had always thought of microreactors as analytic tools. When you only have nanoliters of material, you can detect and process it, separate it, and use it for screening approaches. What Klaus Jensen and co-workers do is actually think about microreactors for production, and so that's one of the things I'd like to show you. We all know one of the beauties of having the so-called lab on a chip is that you can put many functionalities on the same chip, including integrating your detection system so that you can monitor these nanograms or nanoliters of material in an effective manner. You can take all the other unit operations we have, and we're so used to, and now shrink them down and make packed bed reactors, but now your packed bed particle sizes are in the micron size range, heat exchangers, temperature sensors, and of course these microreactors are important for biochemistry and biophysics applications. Klaus Jensen's work is an example of this type of integration of unit operations onto a microreactor scale. He's focused his attention on the problems of mixing that, as we've been are aware, are limited to diffusion on these small scales, but can be aided to provide mixing on time scales that are necessary for chemical reactions. Heat exchangers can be made. The high surface area to volume ratio gives you extremely good heat exchange characteristics. If you have these channels in silicon, run your reacting fluid down the middle, cooling fluids down both sides, and the air gap on the other side, you can achieve extremely good heat exchange characteristics. You can put various sensors on the chip, on the chemical reactor, temperature sensors and optical sensors to monitor reaction progress. What was exciting to me was to think about what this could mean in terms of not just screening and detection and measurement of different catalysts, and measurement of different chemical parameters and different chemical properties. But to think about how microreactors could be used for actual production. And there are two main issues here, two main features of microreactors. One is their small size and their heat exchange capabilities allow you to run reactions under conditions that may be very difficult to achieve on a larger scale. So one can run at temperatures, more extreme temperatures or different temperatures than are available in larger scale, and one can deal with large heat transfer needs from highly exothermic reactions. So that allows one to think about moving into new parameter space for chemical kinetics and chemical reactions. In addition, the idea that one has many materials that are highly dangerous and undesirable to store in your chemical plant, and certainly undesirable to transport from one place to another. As we face increasing issues of security and safety in our chemical plants, one might want to produce a material just in time for the next step in the process. One example of a material highly used in the chemical and pharmaceutical industry is phosgene, which of course is very hazardous, and one wouldn't want to store it or actually its precursors around or could avoid transporting them. It's also an exothermic reaction, and so one can take advantage of these microreactors then to take away the heat and to keep the storage and shipping hazards down. Jensen and coworkers have managed to make a silicon reactor with an oxide coating that is resistant to the chlorine, to operate at a wide range of temperatures to study the kinetics of the reaction, to run it over activated carbon particles with a very high surface area due to the small size of the particles, and then to deal with the heat and mass transfer, which will improve both safety and productivity in this reaction. They can run at essentially 100% efficiency or 100% conversion of chlorine to make phosgene. If they run 10 multi-channel reactors in parallel, they can produce 100 kilograms per year. So you could think about running banks of 10 microreactors in parallel. One of the beauties being if one of them breaks, you just turn it off. You don't have much material to leak if there's a problem, and you can adjust your needs as you need supply. You could then take the phosgenes for another reaction that's needed, and you can do it right at the point where you need it. Microfluidics have also been extremely useful in microreactors for a number of problems in biochemistry, analytical separations, and biophysics. I take this example from Shu Takayama in Michigan as an example of the beauty of microreactors and the way chemical engineers tend to focus on cellular and molecular level problems. One of the issues is that in vitro, one typically studies a bunch of cells all in a uniform composition and uniform conditions because they're well mixed and they're in dilute solution. In actuality, in many natural environments, a high cell density causes gradients, and the gradients in various components may make a large difference in the way the cell operates. Shu Takayama has been able to mimic this behavior with a simple microfluidic cell where he takes advantage of multiple laminar flows and the fact that there won't be any mixing except diffusion to basically present a cell with different conditions on two sides of its structure. He can then position molecules in subcellular regions of a cell and look at how the gradient in that concentration affects the cell function. One of the interesting things he studied was growth factor, and he found that actually the growth factor signaling was localized unless it was overexpressed, as in cancer cells. So you could tell the difference between normal and cancer cells through the way the transport of growth factor occurred and the signaling processes from growth factor occurred across the cell. So these are examples then of how one can now take microchemical reactors or microfluidic devices and use them for biophysics and biochemistry studies. I wanted to talk a little bit about catalysts and zeolites, and I really think that here the marriage between our analytic and computation abilities and our experimental capabilities is key to a lot of exciting developments. Mark Bartow and co-workers at Delaware have taken their vast experience and long history in surface science and combined it with now computational approaches using density functional theory to improve and invent new catalysts. The example he gave me is oxidation of ethylene to produce ethylene oxide. It's an old reaction that's been around a long time, and yet its pathway is actually relatively poorly understood. He was able to do density functional theory calculations of this oxidation on silver to look at what the intermediate structure was between the oxymeta cycle, he calls it, the metal and the organic, and to show that there was actually a difference in the pathways than what was previously expected. And the way he did this was somewhat interesting, combining density functional theory with data from the isotope effect. If you take ethylene or you take purely deuterated ethylene, you find a difference in the selectivity between aldehyde and ethylene oxide production. And from these calculations, you can actually show this kinetic isotope effect really points to a certain intermediate. This intermediate then is really controlling, and so the recognition of the importance of these structures is going to be key to figuring out how promoters and metal organic interactions or intermediates dictate kinetic pathways. Mark Davis at Caltech has worked in the area of zeolites for a number of years, and as you may be familiar, in 1992, researchers at Mobil developed silica-based zeolites with a pore size on the order of 2 to 10 nanometers. Mark Davis has taken that further and developed large pore zeolites in silica with a lot of versatile character to them. These silica-based materials are uniform and are very stable with temperature. He's able to show that both the size and the shape of the pore are important. And by modifying the pore surfaces, he can both change the nature of the molecule surface interaction by making them more hydrophilic or hydrophobic. In addition, he can put catalytically active moieties in the wall of the pore and change the catalytic activity. So he has shape selectivity that comes from the structure of the zeolite pore, and then catalytic activity that comes from the chemical modification to the pore. There are many future opportunities and challenges. He's written a nice article in Nature recently about this, thinking about what kind of inclusion bodies you can put into a zeolite structure, all kinds of interesting applications in separations, making low dielectric materials, using them as magnetic resonance contrast agents, making zeolite dye lasers, and producing nanomaterials of desired structures, such as carbon nanotubes, by choosing the right shape and size zeolite. Finally, my last example will be brief. because I don't know very much about this field, but I'm truly excited by chemical engineers' work on and vast experience with dynamic optimization and process control, and now the interdisciplinary work between chemical engineers and computer scientists and others to develop new algorithms and dynamic optimization for a variety of complex problems. Paul Barton at MIT in particular is applying this systems level analysis optimization and control algorithms to complex biological networks. So he's both developing the tools to interrogate or test network models for biological cascades, for example, signal transduction pathways in a biological process. And then he's collaborating with computer scientists and bioengineers to study a number of fundamental biological processes with the dynamic optimization tools that he has. So what do we have in innovation that I've at least chosen as a snapshot of what I think is exciting in U.S. chemical engineering? We have a move from what I would call mechanical or hard processing of materials to soft processing through self-assembly and nanotechnology. We have a move from batch screening to high throughput that's aided by combinatorial chemistry and microreactors and micro separation devices. We have bioreactors moving to more bioanalytical molecular studies on single molecules or single cells aided by microfluidics. We have design by trial and error. I distinctly remember doing many trial and error problems when I was a chemical engineering student, to a rational design aided by computer computation and computational modeling. And we have control theory moving beyond process control to dynamic optimization problems, including biological systems. So where does that leave us in terms of evolution? I wanted to spend a little bit of time talking about chemical engineering employment, chemical engineering as a major, the curriculum, and the bio question. We all know that chemical engineering employers are a diverse group, and in the next 10 years it's projected that the chemical industry will actually need fewer chemical engineers. So we need to think about how we're training chemical engineers for these other sectors. I have a little bit of data from the AICHE. If you look in these years for bachelor's chemical engineers, about 56% of them went into industry. There were some unknowns and some unemployed, so it's not very good. Only about 10% go into graduate school or professional school, which is something we are concerned with. Of those that go into industry, though, it's interesting to see still quite a number are employed by the chemical industry or the fuels industry, but now you have fairly important sectors from biotech and pharma-related industries, materials, and there's electronics, and food and consumer products. So clearly the chemical engineering portfolio of jobs is quite diverse, and I'm sure if we looked 10 years ago, this pie would have looked much different and much more homogeneous. PhDs then mostly go into industry. A number of them go on to graduate school, which I think means postdoc, unless they just go on to get another graduate degree. And then some 16% go into academia. Of those that go into industry, this is interesting that still a number of them, are about a third, go into chemicals and fuels. Electronics is quite large, and biotech is quite large for the PhD population, and growing. And so one, again, can ask not only about these industries, but even about this thing called chemical. Are the chemical industry employers still employing chemical engineers for the same type of jobs they were 10 years ago. I would say that the portfolio at the DuPonts and Dows and such hiring these PhDs is actually changing, and so because they're in that sector doesn't mean they're not working in one of these other areas. You can take a little more detailed look at data from MIT from our own graduates and see the same kinds of trends that if you look at chemical engineers from the going into chemical process industry, it dropped quite a bit since 1987. You see growth then in the materials science area and in the biotech, biomedical arena, as well as a growing number of chemical engineers going on to a postdoc. And I think that's reflecting this kind of specialization and interdisciplinary nature of chemical engineering. You finish your PhD, think about what you would like to do, and many chemical engineers opt to go on to study yet another perhaps subspecialty or to pursue a postdoc with a colleague in a related field. The consulting and finance thing has gone away. So do we have enough chemical engineers? That's the eternal question, because the chemical industry is shrinking, and are we overproducing them or not? By the diversity of jobs they're going into, probably not. There's been much concern about whether we're having enough students major in chemical engineering. And actually, if you look at recent data, there's a little bit of a downturn, at least in MIT, and I think in a number of universities, and perhaps here. But I'm not particularly pessimistic, because I look at this overall and see these peaks and valleys, and even if we're going down right now, you can relate these all more to societal events and pressures than to anything wrong with the discipline and students not being excited by chemical engineering. I believe here we had an oil crisis, and we gained from the basically the shutdown of the aerospace industry for a while in the late 70s, and so chemical engineering was on an upsurge, and we were making all kinds of alternative energy, syn fuels and such were the rage. We lost a whole lot of chemical engineers then to electrical engineering and computer science as the information age became the exciting thing to do, and chemical engineers, many of them went into that field. We're picking up again, and you could argue that this downturn we're seeing now is a lot of students going into biologically related fields, which I think is what's fueling the decision to address the name change for the major. You can look at MIT again as an example of this, and we actually have relatively stable enrollments with the graduate degrees in particular staying fairly constant, and the number of undergraduates peaking and dropping off. And this was the subject of some concern at MIT as we had come up from picking up from losing them all to the electrical engineers for a while. So where is chemical engineering today? We still have our fundamentals we value very much. We bring those to anything we do. We've added biology to this list, and we really need to face how we need to evolve our approach to both the fundamentals and our core discipline. We need to, I believe, we need to capture the new science and new areas that are emerging, and in some sense readdress our roots in chemistry and our ability to do synthetic work and synthetic chemistry, and make sure we're not losing our connection to chemistry. Meanwhile, bringing in molecular biology and computer science, and so the question is, as brought up earlier, how do we fit it all in? I don't have an answer. I am making a distinction. We have three big trends going on in the U.S., bio, nano, and info, and everyone's excited about these. I believe that biology is a fundamental science, and chemical engineering includes biology as well as chemistry, computation, math, and physics. Nanotechnology is just a manifestation of what we do. I think chemical engineers are good and they contribute to that field along with electrical engineers, material scientists, physicists, and others. But it's not something we're going to change our name to, surely. And information technology is pervasive, and as Dr. Kim pointed out, benefits from chemical engineers who have this ability to span from highly mathematical, highly analytical work to chemistry and biology. What I think is important to realize, though, is that some of the important areas of information technology and computer science are in non-analytic or in fields that we're not traditionally focusing on, such as data mining rather than analysis. So what about Chemi and Bio-E? I decided just to call them that because I didn't want to go through all the particular names. Chemical engineers have been really good at bioengineering. Up to a third of some departments have people who really focus on bioengineering or some part of bioengineering. It spans everything from doing reactor engineering for biological processes, understanding cells as little reactors and using chemical engineering principles there, to protein engineering, directed evolution, real molecular biology, more physical, biophysical work on templates and molecular recognition, making new materials by mimicking biological materials, soft materials and surface science for biophysical problems, and bioinformatics. I chose Charles Cooney's website because it had all these things on it, and I thought it was a nice example of what chemies can do and do already in bioengineering. So, the names. Chemical engineers have a really truly molecular, chemical, and cellular focus, and that's one of the hallmarks of our discipline. We connect math, computation, and physics to both chemistry and biology. We do science and engineering. Should we change our names? I think the best arguments I've heard for that is that for many places it reflects what they're already doing and that they're intent on attracting students. And you could look at it as a problem-directed evolution and trying to speed up evolution by changing the name. So I think there's room for name changes. There's a little bit of a nomenclature problem going on. So maybe Chemi and Bio-E would be. So I'd just like to summarize by saying I feel that chemical engineering is a vibrant discipline. It was a pleasure to get information from a number of colleagues around the U.S. And exciting to think about all the great things that are going on in chemical engineering. We clearly have a central role in many new and emerging technologies. We've evolved from the petrochemical industry. We're involved in many different fields. And I believe our innovations are evolving the research landscape as we go to molecular, analytical, and rational research areas. We have a core that defines our discipline. I think we need to reflect on our strong focus on analysis as we embrace biology and maybe synthetic chemistry a little more seriously. We have sometimes had some difficulties in the discipline because we have a strong tradition of being able to solve everything with a mathematical equation and name a dimensionless group to go with it. Less analytical sciences are hard to quantify and hard to put into. And so it's a challenge, and I think we're working on this. today. I feel we need to include biology, we need to include synthesis, we need to include information technology and remain interdisciplinary. And so one could take the approach that students will choose their specialization as they are in graduate school. Perhaps chemical engineers more and more will be pursuing postdocs as they find that they've gotten interested in another field and they would like further training. But I do think it's an exciting time to be a chemical engineer. Thank you very much.